Brianchon theorem was? Brianchon theorem? So it's like you have a hexagon, right? Inscribed inside of a circle. Really? Brianchon. Now Brianchon, you were here. Pretty sure he was. Because if he wasn't here, who else would have laughed at that joke?
Yes.
But I don't think he was even here. Was he? Okay, so do you remember this theory? I'm pretty sure you were here. Okay, you only missed one.
Yeah.
So it was on the video, you could have watched it. Alright, so there's one with a hexagon, yeah? Tangent. One, two, okay, the tangents here. One, two, three, four, five, six, yeah? So that's Brian. Brianchon's is, if that happens, then these are all concurrent, yeah? Yeah? And Pascal's one, we just went through that, right? It's collinear, so stuff is collinear when you do this thing, right? Okay. So I want to get from that, okay? I want to show you the relationship between them. Okay. And so this will give you more of an awareness, because it might not look like that, because the labelings might not correspond the same way, okay? Yeah. So, yeah. So basically, what I mean by dual is I want to turn sort of points into lines, lines into points. Yeah? So two lines intersect at a point, yeah? 2 points make a line, yeah? See how the duals to each other? Okay, so basically I want the circle, so this line is tangent at that point, yeah? So I want that to be a point. So, another circle. So I have a line that's tangent at that point. I want a point. So I want a point, yeah? You know? And I want another point here. And having the two tangent lines intersect at a point, I want this point to be the line going through those two points. Yeah? So now I've replaced these two tangent lines and the point of intersection with two contact points and the line joining them. Okay? Whoa. That's like dual, yeah? Okay, I want to do the same for all of them. So this is the line, yeah? So if I got this point here, this point here, and I want the line joining them to be like a triangle, okay? I want this line joining them to be like a square, okay? This one here, this one here. Okay, and then I want to label the ones joining together the same thing, yeah? So, you know, this open thing will now go to a circle here, right? This is now square here. And this is now a triangle, yeah? Okay. So now I want to mark in some lines, okay? So I need the triangles to intersect each other, yeah? So maybe, well, which way is it leaning, you know?
Upwards.
Upwards?
Right.
Yeah?
Yes.
Okay, bear with me here. They're all like parallel.
Oh, you're like that.
Okay, and then say that these ones are not meeting here, yeah?
Yes.
Yeah. So see where the two lines intersect, right, is dual to the line joining the 2 points. Remember that, yeah? So that's why we're doing this, yeah? We're not having some separate side here. It's related. Okay, and then the squares, well, that's looking pretty parallel too. But let's say it goes that way for convenience, okay? And then these 3 lines are collinear, yeah? So remember, concurrent now is dual to collinear. Because 3 lines intersecting at a point is dual to 3 points lying on one line. Yeah? Okay. So I guess now the question is, how do we label the hexagons? But this is obviously the Pascal thing that we know, yeah? So remember it was ACE BDF, right? So we know that we know that ACE BDF. So we know that AD and CB intersect at each other, right?
Yeah.
So one of this is AD and one of this is BC. Right, so this works. So you have like A here, right? So let's try to make that one AD, yeah? Put D here. And this one BC. C. Does this work at all? And then this is BE. Where's the BE? We need a BE. If we need a BE, then we need like that to be BE. Yeah? But if we need that to be BE, then we need this to be like AF. So maybe make this one A. This one D. Yeah? And this be that. Will that work? Yeah, this works, yeah? So DECF, yeah? So that's this point here. DE dot CF. Yeah? That's this one. Yeah? AFEB, right? That's the middle one, yeah? That's here. Yeah?
Yeah.
What's the last one?
AD.
That's the first one we had, right? ABBC.
AD.
Yeah? Hmm. Yeah? That's pretty cool, huh? Yeah, so in one direction, it really is built to that, yeah? So it seems like if we do that, we get back to that. So this seems to be a better theorem. It seems like there's a lot of other combinations of this that we haven't explored even, right? Seems to be a lot of other lines that could be concurrent, depending on different combinations of this. Which is kind of weird. But actually, maybe it's obviously they're concurrent. Like maybe that is concurrent with that.
Yeah.
Yeah. Or is there a non-trivial one, you know?
How about like the opposite ones and then the two opposite sides? Like the opposite vertices and then it's compared with the two opposite sides.
Yeah. Yeah. Is that what I said? Like the open circle. Is that what you meant?
Not really. Like you extend the two.
Like this one?
Yeah. Oh no. You extend the
That one?
yeah. And then you extend it to opposite side on either side.
Oh, like this one?
No, like on each side. Yeah.
This one?
Yeah.
Oh,
And then
that's clever, huh? That's pretty cool.
yeah, because that uses
Yeah. Yeah, I guess, did you want to try it? Try it for the normal labeling? Like convex labeling? So you start with Pascal's, yeah, with the normal labeling. Yeah. Okay, so what would be like the dual of that? Yeah, it's the 2 points. This is the intersection of these 2 lines, right? At that point now becomes a line, yeah?
Yeah.
So the point on the circle now becomes a tangent line on the circle. CE now becomes a point. So this line now becomes a point. That's the intersection of these 2 tangent lines. So, so this is now, I guess, what would have been A. This is what would have been B, D, F, yeah? Okay, and then we're saying, like, these lines, so AD and BC intersect, yeah? So that means, what does that mean? The lines are meant to be points now. So the line AD should be the intersection of the tangent of A and the tangent of D, right?
Yeah.
So that should be like here, yeah? BC should be the intersection of the tangent of B and C.
Wait, shouldn't it be opposite?
Huh?
Like opposite side?
Opposite sides? Are you talking about this or this?
No.
This one?
Yeah.
What's the problem?
Like shouldn't the points of intersection be between opposite? Oh yeah, I guess it doesn't matter. Wait, what's the third one then?
The third one.
Yeah.
For what?
The third.
The third point. You mean the red lines?
Position, yeah.
Oh, so I'm going to draw a line joining them. Yeah.
Yeah.
So this line, yeah, corresponds to this point.
Oh.
Does that make sense? Because those 2 points correspond to those 2 lines.
Yeah.
Line joining the points corresponds to the point.
Yeah, that makes more sense.
Okay. Let's do purple, orange, orange. So now we're gonna do this. Orange looks too much like that, doesn't it? Light blue,
Yes.
but then it looks like purple. Light blue, yeah. So CF. But C is here, F is like here. So it's like somewhere off the page, yeah?
Yep.
And then DE, that's E, that's D. That's going to intersect somewhere off the page, and it's like the line that's joining them, yeah? To this point. Yeah? Okay. Okay, and then the last one, we'll do it in purple. So it's this one. A is here. F. Ooh. It's a parallelogram. Parallel bastard.
Oh boy.
Okay, let's say it's over here, okay? This is A, yeah?
Yes. Bit dodgy. Just a little bit.
Okay. And B and E. B and E.
This does not look very current.
Oh, it's not too bad.
You go off this up. You go down.
This is not exactly straight. And that they meant to all. They intersected the line of infinity. At the point of infinity. Yeah. Wait, but were those the ones that you said, right? That's the thing you should have picked up on.
Yeah. Wait.
Remember what you said?
Did I?
You said the opposite side, yeah?
Really?
So are we going across the opposite sides now? Yeah?
Yeah.
Yeah?
Yeah.
So this is kind of like what you said.
Yeah.
So maybe that is. Maybe that's probably actually Brianchon's thing with different labelings with hexagons as well, right?
Yeah.
Because you don't have to label the hexagons like that, do you? Yeah. So maybe we only remembered it for the convex one. See? Because there's like 120 hexagons for the Pascals, right? There'll be 120 here as well, but we only remember one. That's what made it so curious.
Yeah.